setup for our titration. I've already rinsed my burette with distilled water and with portions of solution A. I have also rinsed my pipette already with distilled water and portions of solution B. So what I do is, I'll take my solution A, you see the inscription A on it, then transfer it into my burette. I take off my funnel. Do you see some small drops over here? So if I should leave the funnel inside my burette and adjust my solution, these drops could add to the solution already in the burette and increase its volume. So I have to take it off before I adjust the volume of the solution in the burette. So I adjust to the 0th mark. As it stands, I'm not reading at eye level. So what I'm supposed to do is to bring it down a bit so that I can get the eye level reading. Now I have the bottom of the meniscus sitting on the 0th mark. Now this solution, I would have to discharge it. So I have my solution on the 0th mark when I read at eye level. I'm not supposed to read from below. I'm not supposed to read from above. I'm supposed to be at eye level. Then I'll pull my burette up a bit so that I can get enough room to place my conical flask. So this is my conical flask, which will serve as my titration flask. I take my pipette. This is solution B. So I take 25 centimeter cube portion of solution B using my pipette. I have the bottom of the meniscus also sitting on the mark over here. So I transfer it into my conical flask. And I allow it to drop gently by gravity. I don't blow air through my pipette because the air could contaminate my solution. So I wait patiently for all the solution to be released into the conical flask. I do have some few drops at the tip of the pipette. So I just gently hit the bottom of my conical flask with the tip of the pipette to discharge those small drops. That's it. Then I add 2 to 3 drops of my indicator. You know, these indicators are organic acids and organic bases. So it's appropriate to add 2 or 3 drops only, no more, because the more you add, the more you cause interferences in our titration. And that could affect our titer value. So I added 2 drops. I swirl and I get a yellow solution. So I start with my titration, releasing the acid into the conical flask containing my base with my methyl orange indicator. When performing the titration, please look down here. Don't look up here. We are looking for a color change. And the color change will be seen in the conical flask, not in the burette. So always make sure your eye is down here. The color has changed. So I take my reading on the burette at eye level. 20.90 centimeters cube. That's what I'm getting. 20.90 centimeters cube. The reading is taken at where the bottom of the meniscus sits. So when you look at it, you see the meniscus starts somewhere around 20.70, but its bottom sits on the 20.90 mark. That is my first titration. My initial was 0.00, and my final is 20.90. There's a possibility that I have overshot my endpoint. So in performing my second titration, this is what I'm going to do. I'm going to pipette my base, add my methyl orange indicator, release the acid from 0 to around 16. Then I'll swirl. Then I'll go dropwise. Then I'll swirl. Dropwise, then I swirl until I catch my actual titer value. That is how I'm going to perform my second titration. And I'm supposed to get the actual titer value then. Let's see how it's done. I could choose to continue from here for my second titration, or I could top up to my 0th mark and start from that place again. I'll be speeding up. Then I pipette my solution B. my 2 drops. Then I release from 0 to around 16. Then I swirl. Then from here, I'll move dropwise as I continue to swirl. If you use your own intuition to determine where you're going to release up to, and you release and you swirl, and you realize that the color has already changed, it means that the actual endpoint is even below where you released up to. So use your intuition once again to do the titration all over again, but this time, reduce where you release up to. That's it. So mine, fortunately, the color didn't change. That means I've still not gotten to the end point. So my intuition was right. A drop, then I swirl. The color has changed. Then I check my volume again. .90 again. So my first titration, I had the actual titer value, and I've still gotten it in my second titration. Then I can do same for the third titration, or I could even choose to ignore the third titration and just use my own intuition to produce a value over there. After all, I'm going to calculate the volume of acid used, the average volume of acid used, using only 2 titer values. So if the first 2 are around the same figure, then that is where my actual titer value is supposed to be. So let's go back to the board and prepare a table for our titers. Okay, in some questions, they will ask you to perform the titration using either 20 centimeters cube or 25 centimeter cube pipettes to take portions of B. In such instances, you need to state the volume of the pipette you personally made use of. So in such cases, you write volume of pipette used. Then you prepare your table. Burette readings in centimeters cube. We have the final, we have the initial, then we have the titer. And the experiment was conducted 1, 2, 3 times. So in our first titration, we started from 0.00 on the burette. Then we ended at 20.90. In our second titration, we began at 0.00 and we had our color change at 20.90. So in our third titration, we will assume we started from 0.00 again and we ended at probably 21.00. The titer will be the final minus the initial. The reason why it is convenient to always start from 0.00 is that with that, there is no need for any calculation. So you just put down the values. All values recorded in our table should be corrected to 2 decimal places. If you look at the burette carefully, it measures 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, and 0.9. There is nothing like 0.15 or 0.23 on the burette. So please, be careful not to write 20.91, 20.92, 20.93, 20.95, 20.98. No, it's all to 2 decimal places. But the second decimal place is just x0. So we look at these values, the titers, and we take any two that are consistent, which means their difference should not be more than plus or minus 0.20. Fortunately, these two, the difference is 0.00, so they are consistent. Even these two are still consistent because the difference is 0.10. But 0.00 is more consistent than 0.10. So we are going to pick these two. So my average volume of A used will be given as 20.90 plus 20.90 all divided by 2. And that will give me 20.90 centimeters cubed. That will be the average volume of A used. These values and the information we were provided in the question. We've been asked to calculate the concentration of excess HCl in A in mole per decimeter cube. Now remember, the excess HCl in A is what we titrated with 25 centimeters cube portion of solution B. So to calculate that concentration, we need to make use of our second equation. That is the equation for the titration. And that is HCl plus sodium hydroxide giving us sodium chloride and water. This is our solution A. This is our solution B. We don't know the concentration of solution A, but we have its volume as our average titer, 20.90 centimeters cubed. For solution B, it's a standard solution, so we have its concentration already in the question, and that is 0.100 molar or mole per decimeter cube. And its volume that was used for the titration is the volume of the pipette. We pipetted 25 centimeters cube. With these parameters, we can simply calculate the concentration of A using mole ratios. According to mole ratio, we are comparing solution A to solution B. From the reaction, we have 1 mole of solution A combining with 1 mole of solution B. So amount of solution A as a ratio of amount of solution B is 1/1. 1 mole, 1 mole. But we know that amount is concentration times volume. So amount of solution A can be replaced with concentration of A times volume of A. Amount of B can be replaced with concentration of B times volume of B, and that is giving us 1/1. When we cross multiply, we have concentration of A times volume of A, giving us concentration of B times volume of B. We don't know this one, CA, but we know VA to be 20.90. CB, 0.100 times VB, 25. So our CA will be giving us 0.100 times 25 divided by 20.90. That will give us the concentration of the excess acid that partook of the titration. 0.1196 mole per decimeter cube. Now that is the concentration of excess HCl that was just titrated with the sodium hydroxide. But this one means that we have 0.1196 moles of HCl in 1 decimeter cube of solution A. So the amount of HCl in solution A, given a total volume of 1 decimeter cube, is 0.1196 moles. Remember, already in the question, we said that solution A is a solution obtained by reacting 4.2 grams of powdered rock sample with 1.00 decimeter cube of 0.180 mole per decimeter cube HCl solution. And it means that 1 decimeter cube of HCl in which the rock sample was dissolved inside contained 0.180 moles of HCl. And that idea will really help us, coupled with this one. So let's move on to II. This is the I part of the question, where we were asked to calculate the concentration of excess HCl in A. Now, II is asking for the amount of HCl that reacted with the 4.2 grams sample of the rock. That reaction was between calcium oxide found in the rock and HCl to form calcium chloride and water. That was our reaction. And in that reaction, the question said we had 4.2 grams of rock, not calcium oxide, of rock sample. Then the HCl, we had concentration of 0.180 molar and a volume of 1 decimeter cube. So the amount of HCl is the concentration of HCl times the volume of HCl. And that should give us 0.18 times 1, 0.180 moles of HCl. So the amount of HCl that dissolved 4.2 grams of the rock sample was 0.180 moles. Out of the 0.180 moles, some dissolved the calcium oxide, some didn't. The amount of HCl that was left after dissolving calcium oxide in rock sample is what partook of the titration. And that gave us 0.1196 moles. So think deeply about it. If 0.1196 moles of acid was left after 0.180 moles of the acid dissolved calcium oxide, then the question is, how much dissolved the calcium oxide? So, amount of HCl that dissolved the calcium oxide in the rock is 0.180 moles minus 0.1196 moles. 0.0604 moles. So out of the 0.180 moles of HCl, 0.0604 moles reacted with the calcium oxide and dissolved it, leaving us with excess moles of acid being 0.1196, which partook of the titration to neutralize the base. And since we now know the amount of HCl that reacted with the calcium oxide, we can relate the moles of HCl that reacted with the calcium oxide with the moles of calcium oxide using mole ratio to calculate the amount of calcium oxide, hence the mass of calcium oxide. Simple. How do we do that one too? Let's continue. We are supposed to look for the mass of calcium oxide in our rock sample. Remember, the mass we have already been given is for the whole rock. And inside the rock, we have calcium oxide. And that calcium oxide was what our hydrochloric acid was able to dissolve for us. So let's look at that equation again. Calcium oxide, 1 mole plus 2 moles of HCl, giving us calcium chloride and a mole of water. We have no idea what the moles of calcium oxide is, but we now know the moles of HCl that dissolved all the calcium oxide. It was what we calculated just recently, and it is 0.0604 moles. So the moles of calcium oxide compared to the moles of HCl is 1/2, because moles of calcium oxide is 1, that of HCl is 2. And we know the moles of HCl, right? So we can put it here so that we can calculate the moles of calcium oxide. So amount of calcium oxide will be 0.0604 divided by 2. And that should give us 0.0302 moles. So if we have the amount of calcium oxide in moles, we can just convert it to grams by looking for something we call molar mass of calcium oxide. And that is giving us 40 times 1 plus 16 times 1. 40 plus 16 will give us 56 grams per mole. And our formula to use is our amount is equal to mass over molar mass. So our our mass will be giving us our amount times molar mass. Then the amount of calcium oxide is 0.0302, multiplying our molar mass of calcium oxide, which is 56 grams per mole. That will give us 1.6912 grams. and that will be approximately 1.69 grams. That is the mass of calcium oxide inside the 4.2 gram of the rock sample. IV of the question says we should calculate the percentage composition by mass of calcium oxide in the rock sample. So percentage calcium oxide is equal to mass of calcium oxide divided by the mass of the whole rock sample times 100%. The mass of calcium oxide is 1.69. The mass of the whole rock is 4.2 times 100%. And that will give us 40.24%. So you see, that's an interesting question. And you could get that one in your practical WASI. Always remember, there are two reactions. And the first one, we are dissolving the impure substance in excess acid or sometimes excess base. Then the remaining acid or base, which one you are going to use, is titrated against a standard solution. So if you use an acid, excess acid, to dissolve your sample, you are going to titrate the excess acid with a standard base. If you use a base to dissolve your impure sample, you are going to titrate the excess base with a standard acid. Thank you.